All right. So we're going to talk about decibels now. So we talked very briefly about this property of sound that I called amplitude, and I said that that usually corresponds to loudness. But loudness is actually a very complicated subject when you're dealing with sound. And in reality, like that's like our stock and trade. You know, if there's a whole lot of things that we care about sound that, you know, we spend a lot of time trying to figure out how to do. But the vast majority of the people that we will work with and collaborate with, most of what they care about is actually loudness. It's just about how loud it is. Okay. All of the other things that are also important, and even though, you know, others that we collaborate with maybe wouldn't admit that these things are important because they don't understand them, but they are important. However, the thing that is most, you know, the most conscious thing for them and for everyone and audiences and everything is really just loudness. So is it loud? And, you know, if you distill down everything that we do to its simplest form, we just make stuff louder. Right? I mean, that's really it. We just make stuff louder. Sometimes we get to make the stuff that we have to make louder. But the making it louder is always part of it, okay? And all of our technology and tools and processes and everything that, you know, over the last 120 years have centered around trying to figure out how to make stuff louder. We don't actually have any equipment that makes stuff quieter. Do you realize that? Think about that for a minute. Can you think of a single piece of equipment we have that makes something quieter? We have equipment that can make things less loud. You know, less louder, right?
Oh, okay.
Like you're thinking, what? A fader, like you can make it quieter, right? Turn it down. It's like, no, you're just making it less louder. Okay? You're not making it quieter. Like if something is already too loud, all by itself, there is no knob you can turn to make it quieter. Okay? So that's a very important concept because very often you will get thrown at you these kind of problems where it's like, hey, can we solve this problem? And because it's a sound problem. And if the problem is that something is too loud, you are not the person to solve that problem because you have zero expertise and zero tools and, you know, whoever is the person that's making the thing that's too loud, right? But you can't make things quieter. But in this context of loudness, it's complicated because in reality there's a really huge difference between the quietest thing that we can perceive and the loudest thing that we can tolerate. Okay? That is actually 1 trillion is the difference. On average, there is about 1 trillion times difference between the quietest thing we can perceive and the loudest thing we can tolerate. And there's a lot of zeros in that kind of number, okay? And I don't know about you, but I don't really like to do math on numbers that have that many zeros on it. It's really hard to keep track of. So when we're talking about decibels, decibels is the method that we have come up with to collapse that 1 trillion range down into, you know, kind of like a range of 120 or so that we can actually work with and use, right? So that's what decibels are. So let's take a look at how this works. Can someone run back and close that door real quick? So this range of loudness kind of manifests itself in a couple of different ways that we're going to talk about, because we constantly transform sound into different forms, right? Sometimes it is air pressure molecules, you know, air molecules pushing and pulling against each other. Sometimes it's that, but then we also transform it into little analog voltage waves. And sometimes those are really low voltage waves, and sometimes they're really, really high voltage waves. Sometimes they're little digital bits. And sometimes it's a electromagnetic wave going through the air. And depending on what form our sound is in, its properties of loudness behave differently. The physics start working a little bit differently depending on which sort of state of being the sound is in. But for now, we're going to start by looking at what happens when we are measuring our sound in an electrical way in terms of its power, which usually we call watts. One of the things that we do is we will take a very low voltage audio signal and put it into a power amplifier, right? And that amplifier amplifies it a lot. Like it goes from being like a volt or less into being many volts, tens of volts, right? Like 70, 80, 90 volts, okay? You put that now kind of voltage up against the load of a loudspeaker, and that voltage is going to be able to do a certain amount of work in pushing and pulling that loudspeaker driver, okay? And that amount of work that it's able to do is measured in watts, okay? So here's what we came up with. Remember, range of a trillion. How do we collapse this? Well, we use logarithms. So if you have learned anything about logarithms before, you will know that a logarithm does basically what the thing I'm talking about. It takes big differences or large values and abbreviates them into smaller values. Okay, and so a decibel is derived this way. You start by making a bell, and a bell is a logarithm of the power you ended up with divided by the power you started with. Okay, so a bell is basically a small number that represents the difference between those two power levels. Okay. So rather than talking about the power in absolute values, in actual watts, that's when you start getting into the really big numbers. We can instead just focus on the difference between where we were and where we are now. Okay? And if we can abbreviate that range, then we can work with smaller numbers. Turns out that just doing a simple logarithm of one power divided by another power doesn't quite collapse that range into a small enough value for us. So a decibel is basically the same thing, just times 10. And what that does is that now collapses it into a range of values that we mere sound people who have a hard time counting past 3 can deal with. Now it becomes 3-digit numbers, which we can do. Okay? Exactly. There's some kind of rules of thumb for how this works. And when you're dealing with power, we call it the 3 and 10 rule. And the idea there is the way that this math works out when you run this math, the kinds of behavior you'll see is that when you double the power, so like if you go from 1 watt to 2 watts, that becomes, you run that math and you get an answer of 3. In other words, 3 decibels. 3 decibels difference between 1 watt and 2 watts. But if you went from 2 watts to 3 watts, you would not get a 3 dB increase. You would get a less than 3 dB increase. So to get another 3 dB, you have to double it again. So you would have to go from 2 watts to 4 watts before you would get 3 dB again. So that first step, where you only had to go up a watt and you got 3 dB, you need twice as many watts to get the next 3 dB, and then twice as many watts to get the 3 dB after that, and twice as many watts to get the 3 dB after that.
Okay, it's a very broad question, but we have been talking
Yes.
I have been at this school.
Yes.
And all I have heard is double the power. You need double the power to get a 6 dB increase.
That is wrong.
Okay, so I'm hearing wrong or people are saying.
Maybe a little bit of both.
Okay, cool.
We will get to this to the 6 thing
Brilliant.
later, but for now we're talking about 3. So when you're talking about power, when you double the power, you get a 3 dB increase. And so you can start to see how this collapses into, it takes a big range and collapses it into a small range. Also turns out, just incidentally, that if you multiply the power by 10, you get a 10 dB increase. You could also divide it by 10 and get a 10 dB decrease. But what you'll see is here's now a chart of how this works. If I just do it in tens, I go from 1 watt to 10 watts, I get a 10 dB increase. But from 10 watts to 100 watts, I get another 10 dB. So now I'm at 20 dB increase. So that I have to do what I did first 10 times more than that to get the same decibel difference, right? Until we get all the way up to 10,000 watts, and now we went from, we've got a 10,000 increase in actual power, but in decibels, that's only a 40 decibel increase. You see how we're taking big numbers and big differences and collapsing them down into smaller ranges? But to further drive it home, that 10,000 difference that got us 40 dB, we do that again, that exact same thing again, and we only get 3 dB more after that. Exactly. Okay.
Absolutely brutal.
All right. But this is the method we've come up with to collapse these big ranges into smaller values that we can now have conversations about and do easy math on, right? So that's how decibels work, is because I don't like numbers that have that many digits. And this isn't even, and this isn't even a very big number, right? When we start talking about pressure in pascals of air pressure, like the numbers of zeros go way up. And, I just don't like dealing with that. I'd much rather deal with numbers like this, 0 to 43, than 1 to 20,000. Okay? So let's take a look at how this works. So here is just sort of a chart that would show you how this corresponds to different power levels 1 through 10. And this is how you would get, integer decibel ranges. Okay? So look at that for just a moment. And you can kind of see what's going on here. There's you start with 1 watt, you go to 10 watts, and you get a 10 dB increase. 1 watt to 2 watts, 3 dB increase, so on and so forth. Now, let's see what we could do with this math. Don't write that down. So if I were to ask you, using this chart, to figure out what power level in dB is represented by 80 watts? Well, we know that going from 1 watt to 8 watts gets us a 9 dB increase, right? And then we know that going from 1 watt to 10 watts gets us a 10 dB increase. So if we have 9 dB with 8 watts, 80 is 10 times 8, right? So we would get a 10 dB increase on top of that. So now we're at 19 dB. See how that works? Yeah. All right. So what about this? 1 milliwatt. So a milliwatt is 0.001 watts. Okay? So starting at 1 watt, we know that if you multiply by 10, you get a 10 dB increase, according to the chart here. So if you divide by 10, you get a 10 dB decrease. So if we start with 1 watt, and every time we go a 10 dB decrease, we move that decimal spot to 3, 0, 0, 1. So
but if you're already at 0?
So now we are, I'm just counting the number of times that we divided by 10, right?
Okay.
We divided by 10 3 times, right?
Yes.
So we start we start at 1 watt and we go to 0.1 watts, and that's a 10 dB decrease. Then we go to 0.01 watts. It's another 10 dB increase. Now 0.001 watts, and now we're another 10 dB increase. That's a total of 30 dB.
Oh.
So
Okay.
1 milliwatt would be otherwise known as minus 30 dB in this scenario. Okay? Now, what about 4 milliwatts? Okay? Well, we know that 1 milliwatt is minus 30 dB because we just figured that out. So if we multiply 1 by 4, what does that get us? That gets us a 6 dB increase according to our chart. So what would be a 6 dB increase from minus 30 dB? Yeah, minus 24 is 4 milliwatts. See how that works? I'm just showing you this how this math kind of works when you're collapsing this with logarithms, okay? So here is the challenge, just to see if we've driven the concept home. Can we recreate that chart using that 3 and 10 rule? Doesn't matter. You have to figure out how to get those numbers.
Okay.
So how do we recreate this chart using only the 3 and 10 rule? You can't actually do a logarithm on your calculator. I know it's possible to. I'm saying I'm not going to let you. So assuming that we start with 1 watt and that equals 0, how do we figure out all of these other numbers using only that 3 and 10 rule?
So twice 1 is 2, which is 3. And then we can...
So you're saying if we take that 1 watt, multiply it by 2, we get 2 watts. That would be a 3 dB increase, right? So 2 watts would go there. Yes.
And then to get to the 10
To get to the 10 dB, that would be multiplying by 10. So this would be 10 watts, right?
fill in 4 and 6 there. 4 watts would be 6 dB.
So we take that 2, multiply it by 2, and we'll get another 3 dB increase. That would be the 6.
Yeah.
So there's 4 watts.
8 would be 9.
So 8 watts would be another doubling. So that would be our another 3 dB increase. So that would be our 9 dB. Okay, how do we get the rest?
Can you...
We got the easy ones.
Only can't use logs?
No.
Why not?
I see the button right here.
He has the button.
I told you, we have to learn how to do this in our head. Because you're not always going to have the calculator around with you.
Yes.
And you're not going to remember the math anyway.
I don't have a log on my watch, though. Well, this is really basic problem solving, and we're all logging.
It's okay. That's probably because
Yes.
it's also us, and we be like that.
Any ideas?
So
I heard somebody say it a minute ago. Somebody had the right idea. Okay, how could we use division to our advantage
That's
here?
what I was trying to figure out. Divide
we were doing
4.
it. We're working with the
So the 3 and 10 rule, if we use the 3 and 10 rule, we could divide something by 2 or we can divide something by 10. Which of those scenarios?
Divided by 2?
Yes,
Oh.
right?
3 times.
You divide a power by 2 and you go down 3 dB, right? That's the whole point of the 3 and 10 rule. Okay? So how could we, what's something that we could either divide by 10 or divide by 2 in order to get us some of these other numbers?
Divide 10 by 2.
Yeah, so we could take this 10 watts, divide that by 2, and we will go down 3 dB, right?
Yeah,
So what's 3 dB?
7 dB is 5.
987, right? So that would be 5 watts.
You could divide 5 by 2 there. You get
Yep.
2.5 on,
So 654, that would be 2.5.
divide that by 2 again.
That would give us the 1. 3, 2, 1. That would be
1.25.
And then
okay.
And then we can multiply.
How do we get the other 3 now?
for 6 oh, we already have 6 dB. Just kidding. Hold on.
So we still need 2 dB, 5 dB, and 8 dB.
Is it 3.15 divided by?
Where'd you get 3.15?
Yeah, I already have. I have the previous chart, so I know what sits at 5. I'm just trying to figure out what you divide to get to that 3.1.
Well, could we go down and then back up? Am I overthinking this? But like, if I divide 1.25 until it's tiny and then multiply it by 10?
So,
Divide 3.15 by 2,
Because that
you
makes
get
sense.
1 point.
yeah, but you don't know 3.15 exists yet.
That's true.
Yeah,
You
but-
can't use that number.
Okay.
Yeah.
It's not there.
But if we know that it exists, we can work backwards, and doesn't that still count as problem solving?
No, because you don't know it exists. You have to only use the numbers that are in front of you on the screen right now.
And so you said we could divide by 2 and 10. Can we divide by 3 as well, or yes, no, maybe so?
I haven't taught you how dividing by 3 translates into decibels yet, so no.
8 divided by 2, or 8 divided by 10 is 0.8 times 2 is 1.6, which would take you down by 8 to -1.
Okay.
Up by 3 to 2.
So let's talk through that again. So we're going to take 8 divided by 10 would give us
Yeah.
0.8,
Down and back up.
and that would be
Then multiply that.
that would be what, -1 dB?
Yeah, -1. 0.8 times 2 is 1.6, which would take us to 2 dB.
So then so then we multiply that by 2,
And we can do the same thing with
and that gives us, so what's 0.8 times 2?
1.6.
1.6 dB. And so 3 dB up from that would be 0, 1, 2, right? So there's 1.6, okay?
And then you can do the same thing with 4. Divide 4 by 10 to get us to.
Okay, but why can't you just work with this number?
Oh, because I didn't think of that. Okay, fine. Multiply that times 3 times 2.
Times, so
2.3.4 or 5, 3.4. 2.4. What?
should be 3, it has to be bigger than 2.5. So
Yeah, but 1.6
3.15, right?
is not. 16
Yeah.
times 2 is not.
I know it's 3.2, but
So 3, yeah, so 6 is, so it would be 3.2, right?
Yeah. That
Very good. Okay.
and then
And then 3.2 times 2 brings us to 64, 6.4.
There you go. We did it. So going back now to our chart, you see we were a little, so there's 1.6. We did 3.2.
Yeah.
And the chart said 3.15. This is 6.3. We said 6.4. But guess what? Here's the crazy thing about decibels. Both of those answers are right.
Oh,
Okay.
It's all relative.
Because we're collapsing big ranges into small ranges. So there are many numbers of actual watts that would represent each decibel value. That's the crazy thing about decibels. So close counts, right? Like you could do several rounding errors and still end up with the same value in decibels because, many values fall into that same category of the decibel range, okay? Any questions about that? Does that kind of make sense? Are we getting there? All right, so let's try to do some of this math with a calculator now. So if I was to ask you how much louder is 700 watts than 63 watts? Let me pull out the calculator here and show you how I do that. So basically what I'm saying by this is we're starting with 63 watts and we're going to go up to 700 watts. And I want to know how many dB difference that is. So the math here, remember, is 10 times the log of the power that you ended up with divided by the power you started with. Okay? So P1 divided by P0. So in this case, P1 would be 700 watts, and P0 would be 63 watts, right? So here's how I would run that math on pCalc. So I would do the 700 divided by 63 first. And then I would do, this is a base 10 logarithm, so make sure you do that. Don't do the base 2 or whatever. So base 10 logarithm of that, and I get 1.04, and then times 10, it's a 10.46 dB increase.
Why did you multiply by 10 when you did a base 10 log?
Because that's the formula. 10 times the base 10 logarithm of.
Oh, instead of, yeah. God, I haven't done logs in a while. Right.
Okay. There you go. So 700 watts is 10.5 dB louder than 63 watts, or 10.5 dB more power. It's not necessarily loudness, but sometimes it is. Okay, everybody follow that? Wasn't so bad, right? Okay, let's try another one here. How much louder is 10,000 watts than 3,000 watts? So this would be 10 times the log of 10,000, comma, not period, divided by 3,000. What's that? I know. All right. Anybody want to run that? 10 times the log of 10,000 divided by 3,000? So 5.23 dB.
Oh, somebody has something.
Is that what you got?
Yeah.
Somewhere around there? Okay, there you go. So let's see. Okay, so now let's get into like real deal stuff. So you're out shopping for amplifiers, as you will do a lot in your life. And for some reason, you've got your eyes on an 800 watt amplifier, but you only have the budget for a 350 watt amplifier. So the question here is how much, when you plug that into a loudspeaker and use it, and let that loudspeaker turn it into sound, how much actual sound volume are you giving up by going with this smaller amplifier? Well, this would be 10 times the log of 350 divided by 800, because the 800 is the one you thought you were going to buy, and you're going to do the 350 instead. So what are you going to end up with here?
Yeah, 3.5.
Like 3.5 dB, right? How much is 3.5 dB? Like what is that in actual loudness? Has anyone actually tried to do that game on SoundGym? Yes.
Yeah, absolutely.
So how much is 3 dB? What's that?
About half of what?
Like if you have something in the thing, then you go down by 3. It's like,
Oh, okay.
3 dB is actually the smallest noticeable difference of an average person. So your average human being that has not sat on SoundGym for a year, they are not going to notice a difference that is less than 3 dB, right? So
Yeah, once it gave me a 0.25 and a 0.1.
3 dB is the smallest difference that the average person can barely notice.
Even given like an AB?
Yeah.
Wow.
I mean, they'll notice that it changed, but just barely, right? Yeah. It's like you hardly did anything. You did a little bit.
So it
Okay.
doesn't matter.
So, yeah, I mean, in this particular scenario, just get the smaller amplifier. No one's going to care, right? It's 3 dB.
So why do we then, if a 450 watt difference even then doesn't really affect, why do we even bother manufacturing 800 watt amplifiers?
Well, so remember, the amplifier is just that amount of watts is the amount of work it can do against a specific kind of load, right? The amplifier really is just amplifying voltage, right? It's taking like a volt and turning it into 80 volts or something, right? The amount of watts that turns into depends on what you hook it up to. And so loudspeakers have a couple of properties that determine what happens. One is their impedance. So that loudspeaker is either an 8 ohm load or a 4 ohm load or a 16 ohm load, or maybe you daisy chain them and get it down to like a 2 ohm load or something. But that load, there's that math, that Ohm's law math, that says force against resistance equals X amount of work, right? Watts. That's where you get the actual value of watts, okay? So how much work can that force do against that load? Now there's another then property of a loudspeaker, which is called its sensitivity, that we'll talk about in a minute, and more in a minute. And that is that, so we know how many watts we have, how much work we can do against that loudspeaker, but how much sound does the loudspeaker create for every watt of work that gets done on it, right? And so loudspeakers have a sensitivity that says 1 watt of work on this loudspeaker will net you this amount of audible sound. And that's a moving target. So a big part of what you're paying for when you pay for more money for your loudspeaker is that sensitivity, that ability to make more sound out of less work, okay? So why do we bother making really big amplifiers? A couple of reasons. Because maybe you were too cheap to buy a good loudspeaker. And so now you need to waste a whole lot of energy to make the amount of sound you need on that cheap loudspeaker that isn't very sensitive.
Right.
So it's like you're going to pay the money either way. You're either paying it in a more sensitive loudspeaker, or you're going to have to pay for it in power. The other reason is that we'll get into more in a little bit, is that most of the sound we make gets lost traveling through the air to our listeners' ears. So most of the money you will spend making stuff louder will result in making sound a loudness that no one will ever hear. But you spend most of your money doing that so that by the time it gets to the audience, the amount of sound that is left is the amount that you need. Okay? So we end up making way more sound than we need, like a lot more sound than we need. Like many, many, many times more sound than we need. And that's really expensive. So we spend all of our money to do that just so that we will have enough left over after it all vaporizes in the air, making the trip to the audience. Okay? So this is where the big power amplifiers can come in handy, is not that 3 dB is an earth-shattering amount, but that 3 dB might be the difference between, hitting the level you need in the back row and not hitting the level you need in the back row, given how much you're going to lose traveling that distance, okay? Which we'll get into more in a minute. Okay, so let's try another one here. So what if you need to do this backwards? So this is another common thing. So maybe you're in a scenario and so you have X amount of sound and you need more sound, right? Someone's saying make it louder. And your only option here is to get a bigger power amplifier for whatever reason. So you decide that you need 13 dB more sound. And you're currently using 300 watts to create the amount of sound you have already. So the question is, if I need 13 dB more, how many more watts do I need to get me that 13 dB? Well, the math that you use to convert back to actual watts involves creating what's called a power ratio. And the power ratio is calculated thusly. 10 to the power of the dB value divided by 10.
So the dB that you have there is the dB that you're starting with? Or in this problem, would that be the number 13?
Yes. In this problem, that dB would be the number 13 for reasons that will become more clear in just a moment. So 10 to the power of 13 divided by 10. So how do we figure that out? Well, here's how I do that in pCalc. So I do 13 divided by 10 first, and I get 1.3. And then I hit this little button that says 10 to the x, 10 to the power of x. And I get 19.95. Now, that 19.95 is the power ratio of 13 dB. That is not the answer to our question, however. But that is a magic number. That 19.95 is a magic number. You could multiply any value of watts by 19.95, and you will get an amount of watts that is 13 dB louder. So if you take 1 watt and multiply it by 19.95, you will get a value of watts that is 3 dB louder. If you take 1,000 watts and multiply it by 19.95, you will get a number of watts that is 13 dB louder than 1,000 watts. Okay? So in this case, we have 300 watts. So if we multiply 300 watts by 19.95, we will get a number of watts that is 13 dB louder than 300. So we take 19.95, multiply by 300 watts we already have. We need almost 6,000 watts to get us that 13 dB. That's going to be hard. I would suggest that if it's taking us 300 watts to get us 13 dB less sound than we need out of that particular loudspeaker, 6,000 watts is probably going to push the loudspeaker out of the box. Okay? That loudspeaker probably is not very sensitive, and it's not going to know what to do with that much power.
So in a situation like this where you really do need 13 dB, do you then go back and just like restructure your gain? Or
You have to find it somewhere else. Yeah, if you're trying to find it with a power amplifier, you're dead in the water. You've got it. There's another.
We rework the system and try and find it.
There are other ways to do this. Yes, much more efficient ways of doing this.
Rather than like 6,000 watts.
Yeah, and I think hopefully what you're maybe starting to wrap your head around is the extent to which you have been manipulated by marketing people. Okay, so marketing people really like to put these big numbers of watts on the boxes for sound equipment, right? It is a 3,000 watt system, right? And in reality, that means basically nothing, right? Because 3,000 watts into what? 3,000 watts worth of work on what thing? And how much sound do I get for that 3,000 watts? Because 3,000 watts is not sound. 3,000 watts is work, okay? How much actual sound does that amount of work get me? You could put 3,000 watts into a loudspeaker and get a very little amount of sound if it's a really cheap and crappy loudspeaker. So watts don't mean what you have been conditioned to think they mean. You have been conditioned by marketing people to think that watts actually means something. That means that this is good equipment or loud equipment or whatever, and it doesn't. It doesn't mean that at all. It hardly means anything, actually. All it means is the amount of work that the power amplifier can do into whatever this loudspeaker is you're hooking it up to. So if they say, even if someone says this is a 3,000 watt amplifier, even that is a lie, okay? Because that amplifier all by itself, not connected to anything, does no work. And watts is work. All it really does, all by itself, is amplify voltage. It amplifies potential energy. It's not until you plug it into something that turns into watts. And the amount of watts you get is entirely dependent on what you hook up to it. That thing that the marketing people tell you is a 3,000 watt amplifier is only a 3,000 watt amplifier if you put a very specific sort of thing on the back end of it.
So is that type of thing why like D&B is so hardcore about only use our amplifiers and our speakers?
Not really. It's more about the DSP they put in it. But most professional, reputable manufacturers of power amplifiers, they will not say this is a 9,000 watt amplifier. They will just say this is an amplifier, and they will then give you a chart that says here is various scenarios that would result in different types of and amounts of work that this amplifier could do under various circumstances, right? And so you're looking for your specific circumstance with the specific loudspeaker you're wanting to drive, and you'll find out how many watts you'll get out of that particular amplifier when plugged into that particular loudspeaker. And you pick a different loudspeaker, and you'll get a very different amount of watts, okay? So that's just something to keep in mind. Watts don't mean what you think they mean. So here is another scenario here now that we can use that power ratio idea for them. So pretend for a moment that I've taught you what decibels mean in the air, which I haven't yet. But imagine that such a thing existed, that we could actually measure not just power in decibels, but also other things like air pressure amplitude. Let's assume for a moment that we could measure air pressure amplitude and express it in terms of decibels. Okay? You with me? Can we make that leap? Okay. So the leap I'm asking you to make is that we have a loudspeaker that creates 60 decibels of air pressure amplitude with only 2 watts of power. Okay? And the question here is, how much power would you need to get 98 decibels of air pressure amplitude in that scenario? Okay? So we would need to find out, first of all, how many more dB are we talking about here? So that'd be 98 dB minus the 60 that we already know how to make, right? We already know how to make 60 of those 98. It only takes us 2 watts, right? So how much are we left with?
38.
So I need 38 dB more than I already have, right? So now I need to find out what is the power ratio of 38 dB. I need that magic number. Okay? So 10 to the power of 38 divided by 10. So 38 divided by 10 gives me 3.8. And then 10 to the x, I get 6,309. Now that is the power ratio for 38 dB. That is not the answer to the question, however. So we have to take this number and multiply it by the number of watts we used to get the 60 dB that we subtracted, right? So we multiply, and that was 2 watts. So let's multiply our 2 watts by the power ratio for 38 dB. So we get 12,619 something watts. So now you're starting to think, that maybe I oversold this loudspeaker a little bit when I said, oh, it creates 60 dB with only 2 watts. It's like, well, actually, that's not actually very good. Really good loudspeakers, like, ones that you would pay some decent money for, can make 100 dB with 1 watt easily. Okay, so there you go. How are we doing? We okay? Yeah. Have I left anybody in the dust yet? Okay. So that's power. That's how we express power levels in terms of dB. But power is this outlier that behaves differently than everything else. Okay? And the math for everything that is not power is different. Okay? So power is only... The only time we ever really think about power is between the amplifier and the loudspeaker. The rest of the time, we're dealing with forces like pressure and current and things like that. Okay? Oh, the other time we deal with power is in radio transmission. So with like our wireless mics. So we do think about the amplitude of the wireless transmitters in terms of power. That's the only other time we really think about power, though. The rest of the time, we're thinking about some kind of force, voltage, pressure, current, things like that. And those things behave differently. Those things follow what I will call the 6 and 20 rule. So if the 3 and 10 rule says you multiply a power by 2 and you get a 3 dB increase, and you multiply a power by 10, you get a 10 dB increase, the 6 and 20 rule is the same, it's just different. So in the 6 and 20 rule, if you multiply a force by 2, you get a 6 dB increase this time, as opposed to 3. If you multiply a force by 10, you get a 20 dB increase. And here is our friend, the chart, but in this case, calibrated for force now. So we start, and I've done it in volts in this case. So you go from 1 volt to 10 volts, and you've got a 20 dB difference, and then all the things in between. So from 1 volt to 2 volts, 6 dB increase. 2 volts to 4 volts, 12 dB now. That's another 6 dB increase. 4 volts to 8 volts, another 6 dB. You're at 18, so on and so forth. That make sense? So let's try this now. So what is the level difference in dB between 2 volts and 10 volts? Hang on, I've lost my notes here. Somebody want to try to tackle this?
Like
Given our chart here?
Oh, the level difference would be between 2 volts and 10 volts.
So, well, we can see it right here. Based on the chart, right? 10 volts is 20 dB, 2 volts is 6 dB. So 20 dB minus 6 gives us 14 dB. There's a 14 dB difference between 2 volts and 10 volts. Okay, what about 1 volt and 100 volts?
Well, that'd just be times 10.
Yeah, that's 2 10-to-1 ratios, right? And for every 10-to-1 ratio, we get a 20 dB difference. 40 dB is the difference between 1 volt and 100 volts. Now you're starting to see why power amplifiers are really not the best way to try to make a lot of sound, because it's much more efficient to try to make this difference using some sort of force. Okay? All right, so same deal. Let's build our own chart using the 6 and 20 rule. So starting with 1 volt, we have that. We're going to call that 0 dB.
Okay, multiply that times 6 to get 6. Or multiply that times 2 to get 6. Sorry.
There you go. So double it, and we get a 6 dB increase. That'd be 6
Double it
dB.
again for 4 and 12.
Double it again, then we get 4 volts. That would be our 12.
8 at 18.
And 8 would go there.
Multiply the original one by 10.
Yep, so there's 10 would go there.
Divide 10 by 2 to get us to 5 at 14.
Yep.
And then dividing 5 by 2, 2.5 at 8. 2.5 divided by 2 for 1.25 at 2.
Okay.
And then we could divide 8.
Can I show you an easier way to do it than the way you do it?
Yes, please.
It's actually easier just because we're not good at dealing with decimal values lower than 1. It's like it's an abstraction that, for me, it's hard for my brain. But you could take that 1.25, multiply that by 10, and you would get 12.5, and you would get a 20 dB increase on that, which would be 22 dB, right? Yeah, so now we take that, divide that by 2, we got 6.25 now. 6.25 would go there, 3.1,
Hey, I carried the team on the last table and this one too. You don't.
3.1 what?
What? 6.25, 3.125.
25,
Divided
1.6, right? Ta-da! So the numbers, the actual numbers are the same. It's just the difference in dB changes, right? Okay. Okay. So this is the formulas involved. I'm just using what I'm told are the standard variables for voltage, current, and pressure. Doesn't really matter though. It's just a variable. No one cares. Okay, except for scientists who care about that kind of stuff, and I don't care. But I'm just showing you that the math is the same. So to figure out the dB difference between two different forces, you would do now 20 times the log of the force you ended up with divided by the force you started with. So the math is the same. You just do 20 instead of 10. Okay? And then if you're trying to find the ratios, if you have a dB difference and you want to like work that back into the actual force value, that's 10 to the power of the dB divided by 20 instead of divided by 10. Okay? Other than that, it's basically the same math. You just get a very different result. Okay? So shall we try it? It's the same formula over and over again. You don't have to write them all down. It's like it's the same one over and over again.
Wait, is it really?
Yes.
Yeah, no, I just wrote, I wrote quotation marks going up to the
Okay.
formula.
Even for the ratios?
It's just same thing. It's just 20.
It's just 20 instead of 10.
Yeah.
Anytime you see a 10, that's like
10 to the power of dB over 20. Okay, so doing that math, what would be the dB difference between 2 volts and 63 volts? So this would be 20 times the log of 63 divided by 2. Okay, somebody want to run that on their calculator and see what they end up with? 30 what?
1.1. Oh, no, sorry. I was saying, well, it was in progress.
Oh, yeah, This is 31.5. A log of that turns into 1.5. Times that by 20, you get 30. 30 dB. So 30 dB difference between 2 volts and 63 volts. Yes? So yeah, what Andre was doing is 63 divided by 2 is 31.5. You know, and then the log of that gets you 1.5. 20 times 1.5 gets you, right? Okay. I do think about this a little bit. Okay, so this is kind of a weird question, but what is the dB difference between a 9-volt battery and a AA battery? This is just to show you that decibels aren't sound.
They're just what we use to measure.
It's a comparison. Decibels is a comparison. It's not an actual value, right? It's just a way of comparing one thing against another thing. And you could compare anything and express the difference in decibels. You could compare the number of stink bugs in this building to the number of stink bugs in the building next door, and you could express that in a decibel difference. We have 10 dB more stink bugs in this building than in the other building,
That's
right?
a horrifyingly large amount.
Okay? I don't know. I haven't actually counted them, but it seems like there's a lot. Okay? So let's see. Let's compare a 9-volt battery and a AA battery. Anybody know what the voltage is of a 9-volt battery?
9 volts?
Okay. Yeah. Okay. Probably. What about a AA battery?
1.5.
Yeah.
I
It's
love that, yeah, probably.
it's 1 point. Well, you know, as we have seen, you know, sometimes marketing is not entirely honest with us. So let's do 20 times the log of 9 volts divided by 1.5 volts. Somebody run that and tell me what you end up with. I got 15.56 dB. Anyone else get that? Nora got that? Anybody else? Yeah.
0.257.
So it's 15.5 dB difference between a AA battery and a 9-volt battery. Okay, so here's another little leap I'm going to ask you to make here, because I haven't gotten to this yet, but this is a teaser of what's to come in a few minutes, is that, so imagine there is a thing called dBu, okay, which I will define in a moment, but professional line level is dBu, and what we mean by that is +4 dBu is the nominal operating level of professional equipment, meaning like when your meter goes to unity, when your meter goes to 0, it's probably running at plus 4 dBu, okay? 0 dBu is 0.775 volts. So if you know that, then when your meter goes to 0, how many volts is running through that circuit at that point?
So it'd be 4 times, which would be the 2 times 2, yeah?
Well, we would first need to find the force ratio of 4 dB, right? And that would be 10 to the power of 4 divided by 20. What is that?
Yeah, it'd be 10 to the power, which is
1.58. Okay. So that's your magic number. Multiply any voltage by 1.58, and you will get a voltage that is 4 dB more. Okay. So 1.58 times 0.775 is what? 1.23 volts. So when on most professional equipment, when the meter goes to unity, you got 1.23 volts. That's the voltage of your signal at that moment. Okay. Maybe you don't see how that's important to you, but that might become apparent in a little bit here. But it does drive home that concept that we usually, up until it comes out of the power amplifier, that term, we work with what's called low voltage systems, and this is what we're talking about. I mean, our signals are teeny, teeny, tiny. It's like barely a volt, okay? And we're running that around hundreds of feet all through the building. This little teeny, tiny, very vulnerable small signal, right? Which is why we have to be so careful with it, which is why we have to shield all of our cables, and why we have to worry so much about grounding and worry about interference and all this kind of stuff, and worry about lighting and all that. It's because like our little teeny signal is this small thing that is very small and fragile. It's not very strong. We don't pump it up until the last possible moment, right? Right before we need it to really do something, that's when we amplify it into something big. But until then, we keep it very small for a lot of really good reasons. But just something to keep in mind, that it's very small. That signal running down that XLR line is tiny.
I feel bad.
Okay? Oh, I did that already. Oh, here we go. Okay, so inverse square law. We're doing good here. We're moving quick. Okay. So now we're going to talk about decibels in air pressure, okay? So pressure is a force, yeah? Maybe you learned that in physics class. So pressure, and we know that sound moving in the air is pressure, right? We learned that a week and a half ago, or 2 weeks ago. And so if sound is pressure and pressure is a force, then sound in the air behaves like voltage.
Sorry,
Yes.
before you go on, I just want to make sure I understand kind of the difference between the first calculations we did and the second, which like between force decibels and just decibels, is force decibel is post-transformation into a force, and decibel is like the literal power, like kind of like pre-loudspeaker, post-loudspeaker almost.
Pre-amplifier, post-amplifier. Right.
So the
It's really just a matter of watts.
rule is
Anything that can be expressed in watts
3 and 10.
is 3 and 10 rule. Everything else is 6 and 20. Yeah, so if we start talking about watts, you have to do the 3 and 10 math. Every other time, it's 6 and 20, okay? So including when sound's moving in the air. So here's what's kind of happening. So you've got, this is an attempt to sort of illustrate what's going on here, but somewhere in the center of this sphere that I've attempted to illustrate, you have something that is pushing and pulling on the air, okay? and it's going to be able to push and pull on that air with a certain amount of force, right? And that will correspond to amplitude, right? The extent to which those air molecules get squished together and the extent to which they get stretched apart. Well, if you were to go a certain distance away, which is expressed by this red arrow, and measure the pressure at that distance, it will be less. Why will it be less? Because, well, yeah, you're farther away, but why does making it farther away make it less? No, it's actually that pressure is now being dispersed over a wider area. So you measure it here, and it's one thing. You go a certain distance away, and now it's having to push against a much larger thing because it spreads out equally in all directions. Yeah, it's just spread out thinner. Okay? The pressure itself has not changed. It's just being distributed over a wider area, and therefore if you sample it at any specific spot around that sphere, it will be less pressure because it's just been divided so many times. Okay? Now, if you take, if whatever that distance is for that red arrow, if you double that distance and measure the pressure again, now that pressure has been distributed even wider. That pressure has been distributed even wider, and it will be less still. And the extent to which it lessens, and the way that we could express that in decibels, follows the 6 and 20 rule. So,
is this assuming that, I think the sphere maybe is messing me up, but sound doesn't go in all directions?
it does go in all directions.
What about, like, directionality?
Directionality is actually not really a thing. We pretend that it is a thing, but it is not actually. I mean, loudspeakers are not anywhere near as directional as we imagine them to be.
That much I know.
Okay? I mean, you know, like Chris showed us something at D&B that blew my mind.
Yeah. The speaker?
But the one that was, you know, that was directional down to like 200 hertz or something like that, that's insane, right? Like, I've never seen that before, never heard that before. Sound tends to travel equally in all directions unless you make some effort to confine it in some way. But its natural tendency is to go everywhere. Okay? So if you double your distance away from something that's pushing on the air, that gets measured as 6 dB less sound. If you multiply your distance away by 10, that could be measured and expressed in 20 dB less sound. Right? That make sense? Now, so the math you would use to figure that out is 20 times the log of the distance you started with divided by the distance you ended up at. Okay? And you will know how many dB you lost. So let's do some of that math. All right, so now we're getting into some real deal problems now. This is, remember where I said that we lose most of the sound we make just by traveling through the air? This is why. So here we are, we've got a loudspeaker, and it's creating 100 decibels of sound pressure 3 feet away. Well, when was the last time your audience was only 3 feet away from your loudspeaker?
Rarely.
Hardly ever, okay?
And if so, you should
They're
be
usually,
going 100 dB.
yeah, exactly. So, so there's your scenario. This loudspeaker is creating a whole lot of sound, 100 dB at 3 feet away. But your audience is 30 feet away. So how much sound are they hearing?
No, less than that because it'd be 3. Oh, wait, no, 8 decibels.
Yeah, so remember, so 30 feet is 10 times 3, which would be a 20 dB difference, right? So we would lose 20 dB. So the audience is only hearing 80 dB, right? We're giving up 20 dB in the air. How many watts did it take us to get up to something like 20 dB, right? So we have to do a ton of work to make a whole bunch of sound that no one ever gets to hear because it just vaporizes as it goes through the air. Here's another one. So here's a loudspeaker. This is a fairly average loudspeaker, good professional loudspeaker. Has a sensitivity of 113 dB, 1 watt, 1 meter. What that means is you put 1 watt of power into this loudspeaker and measure the pressure 1 meter away from it, and it will be 113 dB worth of air pressure amplitude. Okay? Pretty good loudspeaker. So how loud will it be with 1 watt at 30 meters away.
So that would be times. Well, you have to do the.
So we have to do 20 times the log of,
1. Yeah. Right?
yeah,
1 divided by 30.
1 divided by 30 for our meters, right? What does that work out to be?
Then 20 log of that. It's 1.3.
So I'm going to lose 29.5 dB. So how loud will it be at 30 meters? 113 minus 29.5, right? Because I have to give that 30 dB up, just making the trip.
83.457.
Yep, 83.46. So the audience gets that. That's what's left over for them after I've made the trip. So now you're starting to understand why big, tall line arrays that can put out 130 dB at 1 meter away, why those are useful. Not that anyone's ever going to hear that 130 dB. It's just that by the time you travel to the other end of the stadium, not much of it is left for the audience to hear. You lose it going through the air. That's the insane thing is, doing big shows in big venues. I mean, you spend tens of thousands of dollars to create massive amounts of sound
That all goes away.
that no one hears, just so that you have enough left over by the time it gets to the audience. That's the craziest part of what we do. Because we make stuff louder, but we have to make it stupidly louder in order for the audience to hear something helpful, right, by the time it gets to them. Unless you could stick the loudspeaker in their ear, right? Then it's easy, because it doesn't have to go anywhere. All right, here's another one. This is an actual loudspeaker that exists out there in the real wide world.
What?
And here is a further real-world question here. So you're trying to put together the sound system, and you're going to the theater, and the theater says, hey, we've got a bunch of these JF100Es. This is what you got to work with. But our amplifiers all blew up, and we need new ones. Okay?
They all blew up?
And so the question here is, that's the loudspeaker you're dealing with. It has a sensitivity of 97 dB at 1 watt, 1 meter. And you are doing a show where you need 100 dB at the audience. The audience needs to hear 100 dB. It's a loud show, really loud show. Okay, so how much power does your amplifier need to be able to do in order to get this loudspeaker to generate that amount of sound at the audience?
Well, could it's just double the.
This is a complicated question, more complicated than you're thinking it is. Okay.
Can you just do the times 10?
Well, because even if you got to 100 dB at 1 meter, then you.
So let's work it through. The first thing I need to find out is if I'm making 100 dB at 10 meters, how many dB do I need to make at 1 meter? More, right?
Yes.
The simple answer is more. Okay? So how much more? Let's find that out. So how much do we lose by traveling 10 meters?
10 dB. No.
20 dB, right? We can do that in our head. So if we want 100 dB at 10 meters, then we need 120 dB at 1 meter. Okay, so that's more. That's a lot more. So if we are making 120 dB at 1 meter, and we want to know how many watts it takes us to get that, well, we don't know. The spec sheet doesn't say how many watts gets you 120 dB. The spec sheet tells you that 1 watt gets you 97 dB. That's all we know. We know that 1 watt gets us 97. We need to know how many watts gets us 120. So what I want to do is I say, OK, I know how to make 97. I only need 1 watt for that. So I'm going to subtract that from the 120 that I need. Right?
So we're really just trying to figure out how to get
However many is left. So what's...
3 more.
Yeah. So we're looking at 23 dB that we don't know how to make. Okay? So how many watts do we need to get 23 dB more sound? Well, it'd be sure one of the ways that would be helpful, things that would be helpful to know is what is the power ratio of 23 dB? So that would be 10 to the power of 23 divided by 10. Yeah, if you run that, you get 199 and a half. That is the magic number that you can use to multiply any power value by, and you will get a power value that is 23 dB more. So what is the number we need to multiply now? Remember, we decided we already knew how to make 97 dB, and we're trying to find out how many more watts we need on top of that. So what was the amount of watts that it took us to get to the 97? 1 watt. So I need to multiply 1 watt by 199.5 so that we will then get 120. So yes, it just so happens that it is still 199.5. You need a 200 watt amplifier to pull this off. That's doable, right? Those amplifiers exist. You wouldn't even have to pay a whole lot of money for that. See how that works? Somebody pay you to figure that out. People in your life would pay you cash money to figure that out.
Cash money?
Yeah.
Oh, you know I need that cash money.
I have been paid cash money to figure that out.
And now you've given us that power.
That's right.
But not any of the cash money, which just
No.
isn't fair. Jason, where's my cash money?
It's 11:11, yo.
Make a wish.
Okay.
For cash money.
Wish for cash money.
So everyone okay with that? Does that process sort of make sense? All right, I think we'll stop there. So we'll pick up on Monday and talk about reference levels, okay? Any questions? Yes, so I will send you today some homework. Do as much of it as you can do with the information I've given you, okay? And come back on Monday and I'll explain how to do the rest of it.